Hello everyone. Quick thought experiment. If you drop your phone and your heavy textbook together, which one hits the ground first? Most of you might guess the heavier one, but no, both fall with the same acceleration. That magical acceleration is called small g, the acceleration due to gravity. According to Newton's law of gravitation, the force on a body of mass m at Earth's surface is F equals g multiplied by m sub e multiplied by m divided by r sub e squared. Now Newton's second law says F equals mg. Compare both equations, cancel out m, and what do we get? G equals g multiplied by m sub e divided by r sub e squared. Its value comes out to be about 9.8 meters per second squared. That means every second, your falling object's speed increases by about 10 meters per second. That's why even a short fall feels so fast. Okay, but here's a puzzle. Earth is not a point, it's a huge sphere. How can we treat all that mass as if it sits at the center? This is where the shell theorem comes in. Imagine Earth as many concentric shells, like the layers of an onion. The theorem says, outside a spherical shell, gravity acts as if all the mass is concentrated at the center. Since we are on Earth's surface, outside all the shells, the total gravitational pull is the same as if Earth's entire mass were at its center. That's why our formula G equals gm e over re squared works perfectly. Isn't it cool that complex layers of Earth behave like a simple point mass from far away? But wait, how do we even know Earth's mass? We can calculate it using its volume and density. Earth's volume is 4 by 3 pi re cubed. Multiply by average density ρ and we get Earth's mass, me equals 4 by 3 pi ρ re cubed. Plugging this into our formula for G, the re squared cancels, leaving G equals 4 by 3 pi g ρ re. So if Earth had uniform density, G would be directly proportional to Earth's radius. In simple words, bigger planets with the same density would have stronger surface gravity. That's why Jupiter pulls so much harder than Earth. Here's the mind-blowing part. With just G, and Re, we can weigh the Earth itself. Rearrange G equals gme over re squared to get me equals g re squared over g. Substitute the numbers. G equals 9.8 meters per second squared. Re equals 6.37 times 10 to the power 6 meters. And G equals 6.67 times 10 to the power minus 11. Crunch the math, and boom, me equals about 5.97 times 10 to the power 24 kilograms. So the next time someone asks you Earth's weight, don't say it's heavy, say it's 5.97 followed by 24 zeros kilograms. But hold on, G is not identical everywhere. First, Earth is slightly squashed, wider at the equator and flatter at the poles. Since G decreases with 1 over r squared, a bigger radius at the equator means weaker gravity there. Second, Earth spins. At the equator, rotation creates an outward centrifugal acceleration. This reduces the effective gravity you feel, almost like a tiny lift against your weight. So G is about 9.832 meters per second squared at the poles and about 9.780 meters per second squared at the equator. Tiny difference, but measurable. So technically, you weigh a little less in Chennai than in Delhi. Physics gives you a free diet plan. Let's put all this into practice. We are given G equals 9.81, Re equals 6.37 times 10 to the power 6 meters, and G equals 6.67 times 10 to the power minus 11. We use the formula me equals g re squared divided by g step by step. Me equals 9.81 multiplied by open bracket 6.37 times 10 to the power 6 close bracket squared divided by 6.67 times 10 to the power minus 11. Calculate it carefully and the answer is about 5.97 times 10 to the power 24 kilograms. That's exactly the accepted mass of Earth, all derived from a simple falling motion near the surface. Isn't that incredible? So let's wrap this up. Acceleration due to gravity is defined as g equals gme over re squared. Thanks to the shell theorem, we can treat Earth like a point mass for these calculations. By linking density and radius, we got another formula, g equals 4 by 3 pi g rho re. Cavendish's measurement of g then allowed us to calculate Earth's mass, nearly 6 times 10 to the power 24 kilograms. And don't forget, g varies slightly with latitude because of Earth's shape and spin. So g is not just a number you memorize, it connects universal gravitation to your daily weight, to satellites in orbit, and to our ability to literally weigh planets. I hope you enjoyed this journey into gravity's secrets. See you next time with another adventure in physics.